You're looking at a crime scene. The victim? An entire planet. Mars once had oceans deeper than the Mediterranean, skies thick enough to breathe, and rainfall that carved canyons into its surface. Then something ripped it all away. Today we're uncovering what really killed Mars. And here is a question. If you could discover the answer to one unsolved mystery in science, which would you pick? Dark matter? Consciousness? Or perhaps something else? Let us know in the comments. I will pin the most creative answer. Now let's begin. 4.5 billion years ago, both Earth and Mars emerged from the same cosmic cloud of dust and gas. They were siblings, born from the furnace of the early solar system. Back then, our sun was younger, more volatile, blasting both worlds with intense radiation and ferocious stellar winds. Yet despite these harsh conditions, something miraculous happened on both planets. They developed atmospheres, they held onto water. They became worlds where chemistry could dance, where molecules could become complex, where the ingredients for life could gather and wait. Mars, smaller than Earth but still substantial, spun beneath a protective blanket. Its core churned with molten metal, generating a magnetic field that wrapped around the planet like an invisible shield. This wasn't just any shield, it was Mars's lifeline, deflecting the relentless barrage of charged particles streaming from the sun. Beneath this protection, the atmosphere thickened. Carbon dioxide, nitrogen and water vapor swirled together, creating pressures perhaps similar to what we experience on Earth today. Imagine standing on ancient Mars during this era, roughly 3.5 to 4 billion years ago, during what scientists call the Noachian period. Above you, clouds would drift across a sky that might have appeared blue, scattered light filtering through a genuine atmosphere. The temperature would hover around levels where water remains liquid, not the brutal -60 degrees Celsius we measure today. Beneath your feet, the ground would feel different too. Not the rusty, oxidized dust we associate with modern Mars, but darker soil, mineralogically diverse, chemically active. Rivers flowed during this time. We know this not from speculation, but from the geological evidence that remains etched into the Martian surface. NASA's Mars Reconnaissance Orbiter, which has circled the red planet since 2006, has photographed intricate valley networks spreading across the ancient highlands like the veins on a leaf. These weren't formed by catastrophic floods alone, though those occurred too. Many of these channels show the branching patterns characteristic of rainfall erosion, the kind that develops when water falls from the sky consistently over long periods. The Mars Science Laboratory, better known as Curiosity, touched down in Gale crater in August of 2012. This wasn't just any crater. Scientists chose it specifically because orbital observations revealed something extraordinary: a mountain of layered sediments rising 5 kilometers from the crater floor, named Mount Sharp. As Curiosity has climbed the lower slopes of this mountain over the past 13 years, it has discovered rounded pebbles, the kind that form when stones tumble in flowing streams. It has found mudstones, rocks that only form when fine particles settle in standing water. It has identified clay minerals which require prolonged interaction with liquid water to develop. In October of 2024, Curiosity made another crucial discovery in Gale crater. The rover measured the isotopic composition of carbonate minerals, essentially rocks formed through chemical reactions involving water and carbon dioxide. What the instruments revealed was fascinating and troubling. The carbon isotopes in these minerals suggested extreme evaporation, pointing toward a climate that could only support liquid water temporarily in transient episodes rather than permanently. This finding, published in the Proceedings of the National Academy of Sciences, indicated that even during Mars's wetter past, the climate was already becoming unstable. But perhaps the most stunning evidence comes from a different kind of investigation altogether. In January of 2025, researchers published findings in Nature Geoscience that combined climate modeling with photochemical simulations, all constrained by existing observations from multiple Mars missions. Their work revealed something remarkable. Mars experienced episodic warm periods with an integrated duration of roughly 40 million years. These weren't continuous. Instead, they were discrete events, each lasting at least 100,000 years, driven by hydrogen outgassing from crustal hydration and volcanic activity. During these windows, the atmosphere thickened enough and temperatures rose sufficiently for liquid water to exist on the surface. These warm episodes explain the valley networks perfectly. Rivers don't need to flow for billions of years to carve channels, they just need enough time and enough water. 100,000 years is plenty for erosion to leave its mark. 40 million years total spread across multiple events during the Noachian and early Hesperian periods creates exactly the geological record we observe today. So Mars had water, it had an atmosphere, it had warmth. For a window of time measured in millions of years, it possessed the fundamental requirements for life as we understand it. Microorganisms could have emerged in those ancient lakes and rivers. They could have metabolized, reproduced, evolved. Perhaps they did. We haven't found definitive proof yet, but the possibility remains tantalizingly open. The ingredients were there, the conditions were present, the chemistry was favorable, and that makes what happened next even more heartbreaking. Because something went catastrophically wrong. The magnetic field that had protected Mars for hundreds of millions of years began to fail. Deep inside the planet, in the churning core, where molten iron generated that protective shield, something changed. The dynamo weakened, perhaps the core cooled too quickly, perhaps the convection patterns that drove the magnetic field became unstable. We're still piecing together exactly why it happened, but the result is unambiguous. By around 4 billion years ago, Mars's global magnetic dynamo shut down. Now you might think that losing a magnetic field would be bad but manageable. After all, Venus has no global magnetic field, yet it maintains a crushingly thick atmosphere. But here's where size matters and where Mars's fate was sealed. Venus is nearly as massive as Earth. Its gravity holds on to atmospheric gases tightly. Mars, by contrast, is only about 11% of Earth's mass. Its gravitational grip on its atmosphere was always more tenuous. When the magnetic field collapsed, Mars became naked to the solar wind. This wind isn't like the gentle breeze you feel on a summer day. It's a supersonic stream of charged particles, protons and electrons racing outward from the Sun at speeds between 300 and 800 kilometers per second. When these particles slam into an unprotected atmosphere, they don't just bounce off, they interact. They energize atmospheric atoms and molecules, they strip electrons away, creating ions, and once atoms become ionized, they respond to electromagnetic fields. The solar wind doesn't just blow past Mars, it grabs the ionized atmospheric particles and drags them into space. If you're finding this journey fascinating, hit that subscribe button and give this video a thumbs up. Your support helps this channel grow and allows me to keep bringing you the latest discoveries from across the universe. NASA's MAVEN mission, which stands for Mars Atmosphere and Volatile Evolution, arrived at Mars in September of 2014 with one primary objective: understand how Mars lost its atmosphere. For over a decade now, MAVEN has orbited the red planet, measuring the upper atmosphere, tracking how ions escape into space, and monitoring the interactions between Mars and the solar wind in real time. The data MAVEN has collected tells a story of ongoing atmospheric theft. Every single second, Mars continues to lose atmosphere to space. Under normal solar conditions, approximately 100 grams of atmospheric gas escapes every second. That might not sound like much. After all, what's 100 grams? Less than a can of soda. But time is relentless. Scale that up over billions of years, and you're talking about oceans worth of water, atmospheres worth of gas, all stripped away, atom by atom. But the losses aren't constant. When solar storms erupt, when coronal mass ejections slam into Mars, the escape rate skyrockets. MAVEN has witnessed these events firsthand. During particularly intense solar storms, atmospheric escape can increase by factors of 10 or even more. The early sun was far more active than it is today. 4 billion years ago, solar storms were more frequent, more powerful, and more devastating. Young stars are violent, and Mars bore the full brunt of that violence without its magnetic shield. In March of 2017, MAVEN scientists published groundbreaking results that quantified just how much atmosphere Mars has lost. By measuring the ratio of different argon isotopes in the current atmosphere and comparing them to what the ratio would have been originally, they calculated that approximately 65% of all the argon that ever existed in Mars's atmosphere has been lost to space. Argon is particularly useful for this calculation because it's a noble gas. It doesn't react chemically, it doesn't get locked into rocks. The only way it disappears is by escaping to space. If 65% of the argon is gone, then similar percentages of other atmospheric gases have vanished as well, including the carbon dioxide that provided greenhouse warming and the water vapor that fell as rain. More recently, in May of 2025, researchers published the first direct observations of atmospheric sputtering at Mars in Science Advances. Using over 9 years of MAVEN data, scientists finally captured this elusive process in action. Sputtering happens when high-energy solar wind ions collide with atmospheric atoms so hard that they knock them free from the planet's gravitational pull entirely. The measurements revealed something shocking. Sputtered escape rates of argon are over 4 times higher than previous models predicted. During a solar storm that MAVEN monitored, the sputtering rate increased dramatically, offering us a glimpse into the intense conditions that would have been routine during the early solar system when the sun was younger and angrier. Let me paint you a picture of what this means. Imagine you're standing on Mars 4 billion years ago, just as the magnetic field dies. For hundreds of millions of years, that field had held back the solar wind, creating a protective bubble around the planet called a magnetosphere. Within that bubble, the atmosphere existed in relative safety. But now the shield flickers and fades. The solar wind, no longer deflected, begins to penetrate directly to the upper atmosphere. At first, the changes might be subtle. The uppermost layers of the atmosphere start to heat up as solar wind particles transfer their energy through collisions. Atmospheric atoms gain enough velocity to escape. The density at high altitudes begins to thin. But the planet still has plenty of atmosphere. The losses are gradual. Life, if it exists in the lakes and rivers below, might not notice anything wrong for thousands of years. But the process is accelerating. Here's where things get particularly interesting and perhaps counterintuitive. You might assume that having no magnetic field is the worst-case scenario for atmospheric loss. But research published in the Journal of Geophysical Research in 2020 revealed something surprising. Simulations showed that a weak magnetic field, like the crustal remnants Mars retained after its dynamo shut down, can actually bleed atmosphere faster than having no magnetic field at all. How is that possible? It comes down to the geometry of how magnetic field lines interact with the solar wind. A strong planetary magnetic field creates a robust magnetosphere that genuinely shields the atmosphere. The solar wind flows around this protective bubble, never making direct contact with the bulk of the atmosphere. Earth benefits from this arrangement. Our magnetic field extends tens of thousands of kilometers into space, creating a safe zone where our atmosphere can exist without being constantly battered. With no magnetic field at all, the solar wind does strip atmosphere away through direct interaction, but the process has limitations. Atmospheric loss occurs primarily through a mechanism called ion pickup, where atmospheric particles that drift to high altitudes become ionized and get swept away. But with a weak magnetic field, something insidious happens. The crustal magnetic fields on Mars create small, localized magnetic bubbles scattered across the surface, particularly in the ancient southern highlands where the crust is most strongly magnetized. These weak fields can't create a proper magnetosphere. Instead, when the solar wind encounters them, it drapes around them, bending and stretching the magnetic field lines. Those stretched field lines create channels, essentially highways, along which ionized atmospheric particles can accelerate and escape. The weak magnetic field, rather than protecting the atmosphere, actually facilitates its removal. The simulations showed atmospheric ion loss rates 6 times faster with a weak magnetic field compared to no field at all. Mars was caught in the worst possible configuration. It had just enough magnetic field to make things catastrophically worse, but not nearly enough to provide genuine protection. As millions of years passed, the atmospheric pressure dropped. When atmospheric pressure decreases, the temperature at which water boils decreases as well. Water that could exist as a stable liquid under higher pressure begins to boil away even at cold temperatures. The lakes start to evaporate, the rivers flow less frequently. The climate shifts from episodic warmth to persistent cold. Speaking of what Mars became, if you're wondering about the practical implications of all this history, about what conditions are actually like on modern Mars and what we'd face if humans tried to live there, I have another video exploring exactly that, called "What Would Life on Mars Really Be Like?", where we dive into the challenges and realities of the Martian environment today. The link is in the description, and I think you'll find it complements this story perfectly. But let's continue with what happened to transform the planet. The water didn't just vanish instantly, much of it soaked into the ground, freezing into the subsurface as permafrost. Some became chemically bound to minerals through hydration reactions, locked into the crystal structure of rocks. The Mars Reconnaissance Orbiter has detected extensive ice deposits beneath the surface, particularly at high latitudes. Radar instruments can peer through meters of soil and dust, revealing layers of water ice mixed with regolith. These represent the frozen remnants of Mars's hydrological cycle, water that went underground and never came back up. But a substantial amount of water was lost to space entirely. Water molecules in the upper atmosphere were broken apart by ultraviolet radiation from the sun through a process called photodissociation. The molecule splits into hydrogen and oxygen. Hydrogen, being the lightest element, escapes to space most readily. Oxygen, heavier and harder to remove, mostly stayed behind, and here's where the planet's signature red color enters the story. With abundant oxygen available and no life-producing reducing gases to counterbalance it, the Martian surface began to oxidize. Iron in the rocks rusted. Over millions of years, the entire surface transformed into the oxidized, reddish landscape we observe today. Mars turned red because it was dying. The color is rust, a chemical tombstone marking where water once flowed. The measurements tell us that Mars has lost an enormous amount of water over geological time. By analyzing the ratio of deuterium to normal hydrogen in the remaining Martian atmosphere, scientists can calculate how much water has been lost. Deuterium, also called heavy hydrogen, has an extra neutron. It's slightly heavier than normal hydrogen, which means it escapes to space more slowly. Over time, as hydrogen escapes, the remaining atmospheric water becomes enriched in deuterium compared to the original ratio. Current measurements show that Mars's atmosphere has about 5 to 7 times more deuterium relative to hydrogen than Earth's water does. This enrichment indicates that Mars has lost between 80 and 90% of its original water inventory to space. When you calculate what that means in absolute terms, accounting for the water locked in the polar ice caps and subsurface ice, Mars once had enough water to cover the entire planet in an ocean at least 100 to 1,000 meters deep. Some estimates push that figure even higher. Where did all that water go? Some is frozen at the poles, some is underground, but most of it was broken apart and lost, hydrogen by hydrogen atom, to the vacuum of space. Now, as the atmosphere thinned and water disappeared, the climate entered a feedback loop that accelerated the transformation. Atmospheric carbon dioxide provides greenhouse warming. It traps infrared radiation, keeping a planet warmer than it would be otherwise. As Mars lost carbon dioxide to space and to carbonate formation in rocks, the greenhouse effect weakened. Temperatures dropped. This cooling caused more carbon dioxide to freeze out at the poles, further reducing atmospheric pressure. Lower pressure meant water could exist as liquid even less frequently. Less water vapor in the atmosphere meant less greenhouse warming, since water vapor is itself a greenhouse gas. The planet spiraled into a cold trap from which it has never escaped. The polar ice caps we see on Mars today are composed of both water ice and carbon dioxide ice, also called dry ice. During Martian winter at each pole, the temperature drops so low that carbon dioxide literally freezes out of the thin atmosphere, adding a seasonal layer of frost. During summer, that layer sublimates back into gas. But beneath the seasonal carbon dioxide ice lies permanent water ice, especially at the North Pole, where a cap of water ice approximately 2 kilometers thick sites year-round. This represents one of the largest remaining reservoirs of water on Mars, but it's trapped, frozen, unable to participate in any hydrological cycle. The Dorsa Argentea formation surrounding the South Polar region provides additional evidence of how much ice Mars has lost even in relatively recent geological time. This formation, dating to the Hesperian era, roughly 3 billion years ago, appears to be the remnant of an ancient polar cap that may have contained 20 meters or more of water in terms of global equivalent layer. That's water that existed after the Noachian period ended, water that disappeared during the subsequent Amazonian era, which extends to the present day. Even in Mars's middle age, it was still losing substantial quantities of ice and atmosphere. Research published in Icarus in 2026 explored the history of Martian water during the Hesperian and Amazonian epochs. The study examined how water moved between different non-atmospheric reservoirs and continued to escape to space. The combination of polar processes, atmospheric dynamics, and the likelihood that Mars's axial tilt was typically greater in the past than today's 25.2 degrees meant that surface and near-surface water was more abundant and mobile. Even 1 billion or 2 billion years ago, enhanced atmospheric water content from larger polar caps combined with the increased solar extreme ultraviolet flux that was stronger in earlier epochs drove higher rates of hydrogen and oxygen loss to space throughout Mars's history. What's particularly sobering is that this process hasn't stopped. It's still happening right now, this very moment. Mars is still losing atmosphere. The planet is still bleeding water into space. NASA's MAVEN mission continues to measure this ongoing loss, watching as Mars slowly, inexorably, loses what little remains of its once thick atmosphere. In April of 2025, Nature Communications published observations from a unique opportunity in Mars exploration. For the first time, 2 spacecraft from different space agencies were orbiting Mars simultaneously with instruments capable of studying atmospheric escape. NASA's MAVEN and China's Tianwen-1 mission, which arrived at Mars in February of 2021, provided complementary observations of the Martian space environment from different locations. This allowed scientists to distinguish between spatial and temporal variability in ion escape for the first time. What they discovered was unexpected. Under steady and weak solar wind conditions, when you'd expect atmospheric escape to be relatively uniform and predictable, they instead observed dramatic spatial temporal variability. In the hemisphere where the solar wind electric field pointed toward the planet, a configuration that typically hinders ion escape, they detected the transient appearance of escaping planetary ions with high energies and strong escape fluxes. This finding revealed that planetary ion escape at Mars is more unsteady and dynamic than previously understood, even under stable external conditions. The atmosphere doesn't just leak away smoothly, it's being ripped off in irregular bursts and pulses, adding another layer of complexity to the loss processes. Think about the cosmic injustice of it all. Mars and Earth started so similarly, both had water, both had atmospheres, both had volcanic activity replenishing gases. Both were potentially habitable. The crucial difference came down to two factors: size and magnetic field longevity. Earth is larger, which gave it several advantages. A larger planet has a bigger gravitational pull, making it harder for atmospheric gases to escape. A larger planet also has a larger volume relative to its surface area, which means it retains internal heat longer. That sustained internal heat keeps Earth's core molten and convecting, maintaining the dynamo that generates our magnetic field even after 4.5 billion years. Earth's magnetic field is still going strong, still protecting our atmosphere, still deflecting the solar wind. Mars, being smaller, cooled faster. Its core lost heat more rapidly. The convection that drove the dynamo slowed and eventually ceased. Once that happened, the magnetic shield collapsed, and Mars's fate was sealed. The planet's smaller size also meant that even with a magnetic field, it would have had a harder time holding on to its atmosphere over geological time. Without the magnetic field, it had no chance. There's a tragic inevitability to it. Mars couldn't help being smaller. It couldn't restart its dynamo once it stopped. It couldn't pull its escaping atmosphere back from space. The physics was unforgiving, and Mars paid the ultimate price. But here's something to consider, something that fills me with both wonder and melancholy. During those tens of millions of years when Mars had liquid water, when rivers flowed and lakes shimmered, when the climate was warmer and the atmosphere was thicker, life might have begun. We don't know for certain. We haven't found fossils or biomarkers yet, though we're looking. But the conditions were right. The chemistry was favorable. The energy was available. Life emerged on Earth during its early history under somewhat similar conditions. Why not Mars? If life did arise during Mars's wet period, what happened to it as the planet dried out? Did it go extinct completely, every last organism perishing as the water vanished and the cold descended? Or did it adapt? Did it retreat underground, following the water into the subsurface, perhaps persisting in deep aquifers warmed by geothermal heat? This is one of the most profound questions in astrobiology. Could there still be microbial life on Mars today, hidden beneath the surface where conditions might be more hospitable than the radiation-blasted frozen desert above? Multiple lines of evidence suggest liquid water might exist in localized regions underground. Recurrent slope lineae, dark streaks that appear seasonally on Martian slopes, might be caused by briny water flows, though the interpretation remains debated. Radar data from the Mars Express orbiter suggested possible liquid water beneath the South Polar ice cap, though again, the claim is controversial and requires confirmation. NASA's Perseverance rover, which landed in Jezero crater in February of 2021, is exploring what was once an ancient lake fed by a river delta. The crater walls show clear evidence of water flowing in from the surrounding highlands, depositing sediments that built up layer upon layer. Perseverance is collecting rock samples from this ancient lakebed, sealing them in tubes and caching them on the surface for a future mission to retrieve and return to Earth. When those samples arrive, hopefully in the early 2030s, we'll be able to analyze them with the full power of Earth's laboratories searching for any chemical or physical signatures of ancient life. But even if we find evidence of past life or even discover extant life underground, it doesn't change the fundamental tragedy of Mars's transformation. This was a world that had everything it needed. It had the potential to develop a rich biosphere, to remain habitable for billions of years, to become a second living world in our solar system. Instead, it became a frozen wasteland, its water gone, its atmosphere a whisper, its surface sterilized by ultraviolet radiation that now reaches the ground unimpeded. And we can see this transformation recorded in the planet's geology. The Martian surface is divided into regions of different ages, which we can estimate by counting impact craters. Older surfaces have more craters because they've been exposed to bombardment for longer. The ancient highlands, covered with valley networks and showing clear evidence of water erosion, date to the Noachian period. The younger plains, smoother and less eroded, date to the Hesperian and Amazonian periods when water became scarce and eventually disappeared from the surface entirely. The transition between these geological periods marks the progressive desiccation of Mars. The Noachian period, lasting from roughly 4.1 to 3.7 billion years ago, was the wet era. The Hesperian period, from 3.7 to 3 billion years ago, represented the middle phase when water activity declined but hadn't ceased entirely. Massive floods occasionally burst from subsurface reservoirs, carving enormous outflow channels across the landscape. Then came the Amazonian period, beginning 3 billion years ago and extending to the present, characterized by extreme aridity and cold. The Mars we know today is an Amazonian Mars, and it has been this way for the vast majority of the planet's history. That's worth pausing to contemplate. Mars has been a frozen desert for 3 billion years. The wet period, the time when it resembled Earth even remotely, lasted perhaps 500 million to 1 billion years at most. For 75% of its existence, Mars has been the desolate world we observe today. If Martian life ever existed, it has either been extinct for billions of years or has persisted in the deep subsurface, cut off from sunlight, eking out an existence in conditions we can barely imagine. The story of Mars serves as more than just planetary history. It's a cautionary tale about planetary habitability and the factors that maintain it. When we search for potentially habitable exoplanets orbiting distant stars, we look for planets in the habitable zone where temperatures allow liquid water. But Mars teaches us that being in the habitable zone isn't enough. Mars orbits within the Sun's habitable zone, at least according to some definitions. What matters is whether a planet can maintain the conditions necessary for habitability over geological time. Magnetic fields matter. Planetary mass matters. The history of stellar activity matters. A planet orbiting a highly active star, being constantly battered by intense stellar winds and flares, will struggle to retain its atmosphere, even if it has a magnetic field. A small planet will cool quickly and lose its magnetic dynamo. A planet without plate tectonics might not have an efficient carbon cycle to regulate atmospheric carbon dioxide over time. Habitability is multifaceted, dependent on numerous factors that must all align favorably. Earth got lucky. We're the right size. Our magnetic field has persisted. Our distance from the Sun is optimal. We have plate tectonics that recycle carbon. We have a large moon that stabilizes our axial tilt, preventing extreme climate variations. We have Jupiter in the outer solar system, whose gravity deflects many comets and asteroids that might otherwise bombard the inner planets more frequently. Remove any one of these factors and Earth's story might have been very different. Mars didn't get lucky. It was slightly too small. Its magnetic field died too soon. It had no large moon to stabilize its rotation. It didn't develop plate tectonics, though we're still not entirely certain why. Once the atmospheric loss began, nothing could stop it. The planet was doomed by physics, yet despite this grim fate, Mars continues to captivate us. Why? Perhaps because it represents a path not taken, an alternate history of what Earth could have become under slightly different circumstances. Perhaps because the evidence of its watery past makes it feel like a sibling planet, family in a way that Venus, with its hellish surface conditions, doesn't quite manage. Perhaps because buried in its rocks and soil might be answers to one of humanity's deepest questions. Are we alone? The robotic explorers we've sent to Mars over the past decades have revolutionized our understanding. The Viking landers in the 1970s were the first to successfully operate on the surface, conducting experiments to search for life. Although those experiments returned ambiguous results that are still debated, they marked humanity's first direct attempt to detect extraterrestrial biology. The Mars Pathfinder mission in 1997 demonstrated that we could land rovers on Mars and drive them across the surface, exploring beyond a single landing site. Then came Spirit and Opportunity, twin rovers that landed in January of 2004. Their primary mission was planned for 90 days. Spirit operated for over 6 years. Opportunity, incredibly, functioned for nearly 15 years, finally succumbing to a planet-encircling dust storm in 2018 that blocked sunlight from its solar panels. These rovers discovered hematite spherules nicknamed blueberries, formed in the presence of water. They found mineral veins created by water percolating through fractures in rocks. They uncovered gypsum, a sulfate mineral that forms when water evaporates. Each discovery added another piece to the puzzle of Mars's aqueous history. Curiosity, landing in 2012, brought an even more sophisticated suite of instruments. It carries a laser to vaporize rocks from a distance and analyze their composition spectroscopically. It has a drill to extract samples from inside rocks where they're protected from surface radiation. It possesses a miniature chemistry laboratory to identify organic molecules, and it has found them. Curiosity has detected organic compounds in Martian rocks, carbon-based molecules that are the building blocks of life as we know it. Now, organic molecules don't necessarily mean biological origin. They can form through non-biological processes as well. But their presence confirms that the chemistry necessary for life existed on ancient Mars. Perseverance builds on Curiosity's legacy with even more advanced capabilities. One of its most exciting instruments is Sherlock, which stands for Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals. This instrument uses ultraviolet lasers to detect organic molecules and minerals that formed in watery environments with extraordinary precision. Another instrument, Pixel, which stands for Planetary Instrument for X-ray Lithochemistry, can map the chemical composition of rocks in microscopic detail, identifying exactly which minerals are present and how they're distributed. But perhaps Perseverance's most important role is collecting samples for eventual return to Earth. As of April 2026, the rover has cached numerous samples from Jezero Crater's ancient lakebed and river delta. These carefully selected rocks represent different geological environments and time periods in Mars's history. NASA and the European Space Agency are developing the Mars Sample Return Campaign, an ambitious multi-mission effort to retrieve these samples and bring them back to Earth. The current timeline aims for sample return sometime in the early 2030s, though the technical challenges are immense. Why go through all this effort? Why not just analyze the rocks on Mars with robotic instruments? Because Earth's laboratories are incomparably more sophisticated than anything we can send to Mars. We can use mass spectrometers with incredible sensitivity to detect trace organic molecules. We can employ electron microscopes to examine rock structures at the nanometer scale, looking for textures that might indicate biological processes. We can perform isotopic analyses that reveal formation conditions and ages with precision impossible on Mars. Most importantly, we can conduct experiments that no one has thought of yet, using techniques that haven't been invented yet, asking questions we don't yet know to ask. The samples sitting in tubes on Mars's surface right now might contain evidence of ancient life. They might reveal new details about Mars's climate history. They might contain minerals we've never seen before. We won't know until we get them back here and examine them with every tool at our disposal. Meanwhile, other missions continue to orbit Mars, gathering data. The Mars Reconnaissance Orbiter, operational since 2006, continues to map the surface with its high-rise camera, capable of resolving features smaller than 1 meter across. The images it returns are stunning, showing avalanches tumbling down polar scarps, dust devils whirling across plains, and fresh impact craters that appeared since previous observations. Each new crater provides an opportunity to study subsurface materials excavated by the impact, giving us windows into what lies beneath the surface dust. The European Space Agency's Mars Express, orbiting since 2003, carries a radar instrument called MARSIS that can penetrate several kilometers into the Martian subsurface. It was this instrument that detected what appeared to be liquid water beneath the South Polar ice cap in 2018, sparking intense debate. Subsequent observations have complicated the picture, with some scientists suggesting the radar reflections might come from clays or other minerals rather than liquid water. The truth remains unresolved, but the possibility of subsurface liquid water drives much of the current excitement about Mars. The ExoMars Trace Gas Orbiter, which arrived in 2016, is studying the Martian atmosphere with unprecedented sensitivity, particularly focusing on trace gases. One of its primary targets is methane. Previous observations from both orbit and the surface, including detections by Curiosity, suggested sporadic releases of methane into the Martian atmosphere. This matters because on Earth, most methane is produced either by biological processes or by geological activity involving water and rocks at elevated temperatures. Either source would be significant on Mars. However, the Trace Gas Orbiter's observations have been puzzling. It has not detected the methane that earlier measurements suggested should be present. This discrepancy remains unexplained. Perhaps the methane releases are extremely localized, both in space and time, occurring in small bursts that dissipate quickly. Perhaps the earlier detections were artifacts or misinterpretations, or perhaps something about Mars's atmospheric chemistry destroys methane faster than our models predict. The mystery continues, and solving it will require more observations and better understanding of Martian atmospheric processes. China's Tianwen-1 mission represents another nation's successful arrival at Mars. The orbiter continues to study the planet from above, while the Zhurong rover, which landed in Utopia Planitia in May of 2021, explored the surface for nearly a year before entering hibernation due to dust accumulation on its solar panels during winter. The rover found evidence of liquid water activity in its landing region much more recently than expected, potentially within the last few 100 million years. If confirmed, this suggests Mars's water story is more complex than a simple progression from wet to dry, with possible intermittent periods of water availability even in relatively recent geological time. The United Arab Emirates Hope orbiter, also arriving in 2021, focuses on Mars's atmosphere, studying how it changes daily and seasonally. Its unique orbit allows it to observe the entire planet at different times of day, something previous missions couldn't do as effectively. Hope is mapping how dust, water vapor, and temperature vary across Mars throughout its year, building a comprehensive picture of atmospheric dynamics. All these missions from multiple space agencies around the world are contributing pieces to the grand puzzle of Mars. Each observation adds detail, each measurement constrains our models, Each discovery raises new questions even as it answers old ones. We're living through the golden age of Mars exploration, with more spacecraft studying the red planet simultaneously than at any previous time in history. But let's return to the deeper question underlying all this exploration. What does Mars's fate tell us about planetary evolution and the prevalence of life in the universe? If we look at our solar system, we see 3 terrestrial planets that started with potential habitability. Venus, Earth, and Mars all formed with substantial atmospheres and likely had water. Yet their fates diverged dramatically. Venus, closest to the Sun, experienced a runaway greenhouse effect. Its oceans evaporated, water vapor amplified the greenhouse warming, and the planet became a hellscape with surface temperatures hot enough to melt lead and atmospheric pressure 90 times Earth's. Earth maintained stable oceans and a temperate climate for billions of years, developing a rich biosphere. Mars lost its atmosphere and froze. 3 planets, 3 completely different outcomes. This suggests that the habitable zone around a star might be narrower than we'd hope. It suggests that maintaining habitability requires a delicate balance of factors. It suggests that rocky planets might commonly lose their habitability over time, making long-term stable environments for complex life to evolve relatively rare. Or perhaps we're looking at it wrong. Perhaps Mars teaches us that even planets that lose their surface habitability might retain subsurface habitable zones. Life doesn't necessarily require surface conditions. On Earth, we've discovered microbial ecosystems deep underground, kilometers below the surface, living in cracks and pores in rocks, obtaining energy from chemical reactions rather than photosynthesis. We've found life in subglacial lakes beneath Antarctic ice. We've discovered entire ecosystems around hydrothermal vents on the ocean floor, thriving in complete darkness using chemosynthesis. If Earth harbors life in such extreme environments, why couldn't Mars? The Martian subsurface likely contains liquid water in localized regions where geothermal heat keeps temperatures above freezing. Chemical reactions between water and rocks could provide energy for metabolism. Microorganisms could potentially survive there for billions of years, long after the surface became uninhabitable. This possibility drives much of the current debate about planetary protection. When we send spacecraft to Mars, we sterilize them as thoroughly as possible to avoid contaminating the planet with Earth microbes. Not perfectly, of course. Complete sterilization is impossible without destroying the spacecraft, but we reduce microbial contamination to extremely low levels. Why? Because if life exists on Mars, even just microbial life in the subsurface, it would be the most significant biological discovery in human history. It would answer the question of whether life arose independently on another world. It would provide a second example of biology, allowing us to understand which features of life are universal and which are accidents of Earth's particular history. But if we contaminate Mars with Earth life before we search for Martian life, we might never know what we've lost. Earth microbes introduced to the Martian environment could potentially spread, particularly into subsurface regions where conditions might be suitable. Then if we later discover life on Mars, we'd face the agonizing uncertainty. Is this truly Martian life, or is it descended from microbes we accidentally brought from Earth? The planetary protection protocols aim to prevent this tragedy. Different regions of Mars are categorized based on their potential to harbor life or support introduced Earth life. Regions with possible liquid water or other special conditions face stricter contamination controls. Spacecraft that will search for life must be sterilized more thoroughly than those that won't. It's a careful balancing act between exploring Mars effectively and preserving its scientific value. Looking farther into the future, human missions to Mars will face these challenges even more acutely. Humans are walking microbial ecosystems. We each carry trillions of bacteria on our skin, in our gut, in our respiratory system. When humans land on Mars, they'll inevitably introduce Earth microbes, no matter how careful we are. This has led some scientists to argue that we should prioritize robotic searches for Martian life before humans arrive, completing our astrobiological investigations while Mars remains relatively pristine. Others counter that humans on Mars could explore far more effectively than robots, drilling deeper, covering more ground, making intuitive decisions that robots cannot. The debate continues, but time is not on the side of those advocating for a purely robotic approach. Multiple nations and private companies are developing human Mars missions, with ambitious timelines aiming for the 2030s or 2040s. Once humans land, the Martian environment will change irrevocably. Beyond the search for life, Mars offers practical resources that could support human exploration and perhaps eventual settlement. Water ice in the subsurface can be extracted and melted, providing drinking water, oxygen through electrolysis, and hydrogen fuel. The Martian atmosphere, though thin, is 95% carbon dioxide, which can be converted into oxygen and methane fuel through chemical processes. The soil contains minerals that could be processed into building materials, metals, and other resources. Nuclear or solar power could provide energy, though the solar panels would need regular cleaning due to dust accumulation. Living on Mars would be extraordinarily challenging, requiring sealed habitats, spacesuits for any outside activity, protection from radiation, and dealing with the psychological effects of isolation and confinement. But it's not impossible. Unlike Venus, where the surface conditions are utterly hostile, or the Moon, which has no atmosphere at all and no accessible water in most regions, Mars offers a harsh but potentially manageable environment. It's the most human-accessible location beyond Earth in our solar system. Some visionaries dream of terraforming Mars over centuries or millennia, transforming it back into something resembling the planet it once was. The concept involves deliberately warming the planet to release frozen carbon dioxide from the polar caps and regolith, thickening the atmosphere. A thicker carbon dioxide atmosphere would provide more greenhouse warming, potentially raising temperatures enough for liquid water to exist on the surface, at least seasonally. Introducing greenhouse gases far more potent than carbon dioxide could accelerate the warming. Eventually, if conditions became suitable, photosynthetic organisms could be introduced to produce oxygen, gradually making the atmosphere breathable. It's a grand vision, appearing frequently in science fiction. But the reality is far more complicated. Even if we could warm Mars and thicken its atmosphere, the fundamental problem remains. Without a magnetic field, the solar wind will strip away any atmosphere we create, just as it stripped away Mars's original atmosphere. The timescale for this process is millions of years, so a terraformed Mars wouldn't immediately lose its new atmosphere. But it would be temporary in geological terms, requiring continuous replenishment. Some proposals suggest creating an artificial magnetic field for Mars. One particularly audacious idea, presented at a NASA workshop in 2017, involves placing a powerful magnetic dipole at the Mars L1 Lagrange point, a location between Mars and the Sun where gravitational forces balance. This artificial magnetosphere would create a magnetic shielding effect, deflecting the solar wind around Mars just as Earth's magnetic field does for our planet. Computer simulations suggest this might allow Mars's atmosphere to naturally thicken over decades to centuries as outgassing from the surface and subsurface exceeds losses to space. Is this feasible? With current technology, absolutely not. The energy requirements would be enormous, and we don't have the capability to construct or maintain such a system in deep space, but perhaps future technology could make it possible. Perhaps advanced superconducting magnets powered by nuclear reactors or enormous solar arrays could generate fields strong enough. It remains firmly in the realm of speculative future engineering, but it's not prohibited by physics. which means it might someday transition from science fiction to science fact. Whether humanity ever attempts such planetary engineering or remains content with localized habitats under domes or underground, Mars will continue to teach us about planetary processes, habitability, and our place in the cosmos. Every rock Perseverance analyzes, every atmospheric measurement MAVEN records, every radar sounding from orbit adds to our understanding not just of Mars, but of how rocky planets evolve. The story of Mars is ultimately a story about change, about how planets are not static, but dynamic, evolving over billions of years. The Mars we see today is not the Mars that existed 4 billion years ago, and it's not the Mars that will exist 4 billion years in the future. Planets have life cycles just as stars do, passing through different phases as their internal heat budget changes, as their atmospheres evolve, as their surfaces transform through geological and atmospheric processes. Earth is also changing. Our planet has been through multiple dramatically different climate states over its history. The Snowball Earth episodes occurring roughly 700 million and 2.3 billion years ago may have seen ice covering the entire surface, creating a planet that would have appeared white from space. The Cretaceous period, from roughly 145 to 66 million years ago, had no polar ice caps at all, with tropical forests extending to high latitudes and sea levels over 100 meters higher than today. Earth's atmosphere has transformed completely multiple times, from an early reducing atmosphere with no free oxygen to an oxygenated atmosphere after the Great Oxidation Event 2.4 billion years ago, to the precise composition we have today, maintained by the biosphere. The difference is that Earth has maintained surface liquid water throughout its history despite these dramatic changes. The faint young sun paradox describes the puzzle that the early sun was roughly 25 to 30% less luminous than it is today, yet Earth clearly had liquid water and wasn't frozen solid. The resolution involves greenhouse gases, particularly carbon dioxide and possibly methane, which were more abundant in Earth's early atmosphere, compensating for the weaker sunlight. As the sun brightened over billions of years, Earth's carbon cycle adjusted, drawing down atmospheric carbon dioxide through weathering and carbonate formation, preventing runaway warming. Mars didn't have a similar stabilizing mechanism. It couldn't maintain the delicate balance required for long-term habitability. Its smaller size meant faster cooling, earlier loss of volcanic outgassing to replenish atmospheric losses, and insufficient gravity to retain lighter gases. The magnetic field collapse accelerated the crisis, but even with a magnetic field, Mars's long-term prognosis was poor simply due to its size and distance from the Sun. Comparing Mars to Earth also offers perspective on the current climate changes happening on our own planet. Human activities since the Industrial Revolution have increased atmospheric carbon dioxide from approximately 280 parts per million to over 420 parts per million as of 2026. This is causing global warming, sea level rise, ocean acidification, and disruptions to weather patterns and ecosystems. The changes are serious and demand urgent action, but Earth is not becoming Mars, our magnetic field remains strong, our oceans are not boiling away, our atmosphere is not being stripped into space. What we're facing is a modification of Earth's climate within the range of natural variability the planet has experienced, though happening faster than many previous changes and driven by human activity rather than natural cycles. It's a serious challenge requiring global cooperation and technological solutions, but it's not planetary death. Mars teaches us what planetary death actually looks like. The complete transformation of a world from habitable to hostile over millions of years, driven by fundamental physics beyond any conceivable intervention. Yet Mars's story also offers hope in an unexpected way. It demonstrates that understanding planetary processes allows us to read the history, written in rocks and atmospheres. We can look at Mars today, this cold desert world, and reconstruct its ancient rivers, its lakes, its warmer climate. We can calculate how much water it lost and where that water went. We can model the atmospheric escape processes and match our models to observations. Science gives us the power to understand changes that occurred over billions of years on worlds we've never set foot on. That same scientific understanding applies to Earth. We can model our planet's climate, understand the factors that control it, predict how it will respond to various interventions or continued emissions, and develop strategies to manage the changes we're causing. The geophysics and atmospheric physics we apply to understanding Mars inform our understanding of Earth. Planetary science and Earth science are not separate disciplines but complementary approaches to understanding how rocky worlds work. The fleet of spacecraft orbiting and roving across Mars represents not just exploration, but an investment in knowledge with applications far beyond the red planet. The technologies developed for Mars missions drive innovation. The scientific insights advance our understanding. The inspiration these missions provide draws young people into science and engineering careers. The international collaboration required to mount these efforts demonstrates that nations can work together toward common goals. Mars exploration, like all space exploration, benefits humanity in ways both practical and profound. As we look toward the future of Mars exploration, the next decade promises extraordinary advances. The Mars Sample Return campaign, if successful, will mark the first time humanity has retrieved samples from another planet and brought them back to Earth. The technical challenges are formidable. A lander must touch down near Perseverance's sample cache. A small rocket, the Mars Ascent Vehicle, must launch from the Martian surface carrying the samples, something never attempted before. An orbiter must rendezvous with the sample container in Mars orbit, capture it, and seal it inside an Earth entry vehicle. That entry vehicle must then travel back to Earth and survive the fiery re-entry through our atmosphere. Landing somewhere, it can be quickly recovered. Each step presents engineering challenges. The Mars Ascent Vehicle must be compact enough to fit inside a lander, yet powerful enough to reach orbit despite Mars's thin atmosphere, which provides little lift. The orbital rendezvous requires precision navigation and autonomous operations since the light time delay between Earth and Mars, ranging from roughly 3 to 22 minutes each way depending on planetary positions, makes real-time control impossible. The Earth entry vehicle must protect its precious cargo while decelerating from interplanetary speeds, experiencing heating and forces that could damage the samples. NASA and ESA are currently refining the mission architecture, evaluating different approaches to balance risk, cost, and schedule. Current planning suggests launches could occur in the late 2020s, with sample return to Earth potentially in the early to mid-2030s. If all goes according to plan, scientists around the world will eventually have pieces of Mars to study in unprecedented detail. Meanwhile, other missions are being planned and developed. NASA's Mars Ice Mapper, currently in early conceptual stages, would orbit Mars with advanced radar to map subsurface ice deposits in detail. Understanding where ice exists and how much is available is crucial both for scientific purposes and for future human exploration, since water will be an essential resource. The mission would help identify the best locations for human landings where astronauts could extract water from nearby ice deposits rather than carrying all their water from Earth. ESA's ExoMars. Rosalind Franklin rover, originally scheduled to launch in 2020, but delayed due to technical issues and later by geopolitical complications related to its Russian launch vehicle and landing platform, represents another ambitious life detection mission. The rover carries a drill capable of reaching 2 meters below the surface, much deeper than any previous Mars rover. This matters because the Martian surface is constantly bombarded by radiation that destroys organic molecules. Drilling deeper accesses material protected from this radiation, increasing the chances of finding preserved biosignatures if they exist. Japan's Martian Moons Exploration (MMX) mission, scheduled to launch in 2026, will visit Mars's two small moons, Phobos and Deimos. These irregularly shaped bodies, each just a few kilometers across, have puzzled scientists for decades. Are they captured asteroids, gravitationally snagged by Mars long ago? Or are they fragments of Mars itself, blasted into orbit by a massive impact? MMX will study both moons and collect samples from Phobos to return to Earth. Analyzing these samples could reveal the moon's origin, and if their impact ejector from Mars might even contain pieces of the Martian surface blasted into space millions or billions of years ago. China has announced plans for its own Mars sample return mission, potentially launching in the late 2020s, aiming to return samples to Earth around 2030. This represents an extremely ambitious timeline, compressing into one mission what NASA and ESA are attempting across multiple launches. If successful, it would mark a major achievement for China's space program and provide an independent set of Martian samples for study. Private companies are also eyeing Mars. SpaceX, under Elon Musk's leadership, has explicitly stated that enabling human settlement of Mars is a primary company objective. The Starship launch system under development is designed with Mars in mind, intended to be fully reusable and capable of carrying large payloads and eventually cruise to the Red Planet. Musk has suggested ambitious timelines for uncrewed cargo missions in the late 2020s, followed by crewed missions in the 2030s, though these timelines have historically proven optimistic and subject to delays. The technical challenges of sending humans to Mars dwarf those of robotic missions. The journey takes roughly 6 to 9 months each way using current propulsion technology, depending on the trajectory and planetary alignment. Mars launch windows, when Earth and Mars are properly positioned for efficient transfers, occur only every 26 months. This means a human crew would need to spend considerable time on Mars waiting for the return window, potentially 18 to 20 months, unless they're willing to take a longer, less efficient return trajectory. Life support for a crew during the transit and surface stay requires recycling air, water, and waste with unprecedented efficiency. Radiation exposure during the journey and on the Martian surface poses health risks, increasing cancer probability and potentially causing other issues. Mars's low gravity, 38% of Earth's, would cause bone density loss and muscle atrophy during extended stays, requiring exercise countermeasures. The psychological challenges of isolation, confinement, and distance from Earth, with communication delays preventing real-time conversations with family and mission control, would test crew mental health. Medical emergencies on Mars would be catastrophic. A ruptured appendix, a broken bone, a heart attack, conditions readily treatable on Earth could be fatal when the nearest hospital is millions of kilometers away. The crew would need extensive medical training and supplies, essentially carrying a small hospital with them. Yet despite all these challenges, human Mars missions are likely inevitable. Multiple nations view Mars as the next great frontier of exploration, and the prestige of being first to land humans on another planet drives international competition. When humans finally set foot on Mars, likely sometime in the 2030s or 2040s, they'll walk on a surface carved by ancient water under skies that were once thicker and warmer, across landscapes that might have once hosted life. They'll be visitors to a world that died billions of years ago, explorers investigating the corpse of a planet's habitability. It's both thrilling and melancholy to contemplate. But perhaps died is too strong a word. Mars isn't truly dead. It remains geologically active, with occasional volcanic activity suggested by recent volcanic deposits. Its atmosphere continues to cycle carbon dioxide between the poles and the global atmosphere with the seasons. dust storms still rage, sometimes growing to encircle the entire planet. Avalanches tumble down scarps, dunes migrate slowly across basins. Mars is inactive compared to Earth, yes, but not completely dormant. It's perhaps better to think of Mars as dormant, sleeping, awaiting either natural processes over billions of years or deliberate human intervention to potentially wake it. The Sun is slowly brightening as it ages, following the natural evolution of main sequence stars. In roughly 1 to 2 billion years, the Sun's increased luminosity might warm Mars enough for liquid water to return to the surface, at least if Mars still has sufficient atmospheric carbon dioxide to provide greenhouse warming. Of course, by that time, Earth will be experiencing its own crisis as the enhanced solar energy drives increased water evaporation, strengthening the greenhouse effect and potentially leading toward a Venus-like runaway greenhouse effect. The habitable zone around the Sun is slowly moving outward, and in the distant future, Mars might become more habitable just as Earth becomes less so. This is far speculation. Billions of years in the future, long after the current epoch of human history, will have concluded one way or another. But it underscores that planetary habitability is not static but constantly changing, influenced by both internal planetary processes and external factors like stellar evolution. Returning to the present and near future, the search for life on Mars remains the most compelling scientific question driving exploration. If we find conclusive evidence of past or present Martian life, it would revolutionize our understanding of biology's place in the universe. The probability of life arising on a planet, given suitable conditions, would be constrained by the existence of a second independent example. With only Earth as an example, we can't distinguish between two radically different possibilities. Either life arises readily whenever conditions are suitable, making the universe teeming with biology, or life is extraordinarily rare, perhaps unique to Earth, making us alone in an unimaginably vast cosmos. A second example, even just fossil microbes in Martian rocks, would shift the odds dramatically toward life being common. If life arose independently twice in the same solar system on neighboring planets that both had water early in their history, then the implication is clear. Life emerges readily when liquid water, organic chemistry, and energy sources coexist. This would suggest that the galaxy likely harbors billions of inhabited worlds, most hosting microbial life, with perhaps some fraction developing complex multicellular organisms and even fewer developing technological civilizations. But finding that evidence is extraordinarily difficult. How do you prove that microscopic structures in a rock are biological rather than geological? On Earth, we have structures called stromatolites, layered rock formations created by communities of microorganisms trapping and binding sediment. The oldest stromatolites date back roughly 3.5 billion years, providing evidence of early Earth life. But distinguishing biological stromatolites from abiotic layered structures formed purely by geological processes is challenging even with samples you can examine directly in laboratories. Imagine trying to make that distinction using images and measurements from a rover on Mars. Similarly, organic molecules, carbon-based compounds, can form through non-biological processes. Meteorites contain organic molecules synthesized in space or in the meteorite parent bodies through abiotic chemistry. Distinguishing between organic molecules from ancient biology versus those from abiotic processes requires sophisticated analysis. One approach looks at isotopic ratios. Life on Earth preferentially uses lighter isotopes of carbon, so biological organic material has a distinctive isotopic signature compared to abiotic organic material. But abiotic processes can also fractionate isotopes, and without understanding all the possible processes on Mars, we can't be certain that unusual isotopic ratios indicate biology. The most convincing evidence would be finding structures or chemical patterns that have no plausible abiotic explanation. Certain molecular patterns, particular mineral assemblages, or microscopic morphologies might be unambiguously biological, but we don't know what we're looking for exactly. Martian life, if it existed, might not resemble Earth life. It might use different biochemistry, different information storage molecules, different metabolic pathways. It might have left signatures we wouldn't recognize as biological. This is why bringing samples back to Earth is so crucial. We can apply every analytical technique available, bringing the full power of Earth's laboratories to bear. We can slice rocks thinner than a human hair and examine them under electron microscopes. We can use ion probes to measure isotopic ratios in features just microns across. We can dissolve portions of rock in solvents and run the extracts through mass spectrometers, identifying every organic molecule present. We can do dating of different minerals to reconstruct the rock's history. We can look for biosignature gases trapped in mineral inclusions. We can perform experiments that haven't even been conceived yet, using future technology. Even with all that capability, we might not find definitive answers. The samples Perseverance is collecting might simply not contain life or life's remnants, either because life never existed in Jezero crater, or because it existed but left no preserved traces, or because we haven't sampled the right rocks yet. Mars is an entire world. Even with the numerous missions we've sent, we've explored only a tiny fraction of the surface. It's entirely possible that evidence of life exists in locations we haven't yet visited and might not visit for decades. Conversely, we might find something ambiguous, structures or chemistry that could be biological but could also have abiotic explanations. This would launch decades of debate, much like the controversy over the Martian meteorite ALH 84001. This particular meteorite, found in Antarctica in 1984, was identified as having originated from Mars based on trapped gas that matched the Martian atmosphere composition measured by Viking. In 1996, researchers announced they had found potential biosignatures in the meteorite: carbonate globules containing polycyclic aromatic hydrocarbons, PAHs, magnetite crystals similar to those produced by some Earth bacteria, and tiny structures resembling fossilized bacteria. The announcement made headlines worldwide and was even mentioned by President Bill Clinton in a public address. But subsequent research challenged each line of evidence. The PAHs could be contamination from Antarctic ice or formed abiotically. The magnetite could form through inorganic processes. The structures resembling bacteria were much smaller than the smallest Earth bacteria and might simply be mineral grains. Nearly 30 years later, the debate continues, though most scientists now think the evidence is more likely abiotic than biotic. But the uncertainty persists, demonstrating how difficult it is to prove life's presence from subtle traces in rocks. If we find evidence of Martian life, even ambiguous evidence, it will also raise profound questions about the relationship between Earth life and Mars life. One possibility is that life arose independently on both planets through separate abiogenesis events. This would be the most scientifically significant outcome, proving that life can arise from non-living chemistry through natural processes, something we've never witnessed and can only infer from Earth's history. Another possibility is panspermia. Life arose on one planet and was transported to the other via meteorites, blasted from the surface by asteroid impacts. We know this material transfer happens. We have dozens of meteorites from Mars that fell to Earth. Material has undoubtedly traveled from Earth to Mars as well, particularly in the early solar system when bombardment was more intense. If microbes could survive the shock of ejection, the radiation exposure during space travel, the heating during atmospheric entry, and the impact on arrival, they could potentially seed life from one planet to another. This isn't as implausible as it might sound. Some Earth bacteria can survive extraordinary conditions, Staphylococcus radiodurans can withstand radiation doses thousands of times higher than would kill humans. Tardigrades, microscopic animals, can survive vacuum, radiation, and extreme temperatures when desiccated. Bacteria spores can remain viable for thousands or potentially millions of years in dormant states. The interiors of meteorites are protected from radiation and don't experience extreme heating during atmospheric entry. Experiments have shown that bacteria in artificial meteorites can survive simulated impacts. If panspermia occurred, distinguishing whether life arose on Earth and spread to Mars, or arose on Mars and spread to Earth, or arose on some other body and spread to both, becomes important. Comparing the biochemistry of Martian and Earth life would provide clues. If Martian life uses DNA, RNA, and the same amino acids as Earth life, with the same chirality, handedness, it would strongly suggest a common origin through panspermia. If Martian life uses completely different biochemistry, independent origins would be more likely. Of course, all this speculation assumes we find life or life's traces on Mars. We might not. Mars might truly be sterile, might have always been sterile, with conditions never quite suitable for life to arise, despite the presence of water. Or life might have started but gone extinct so long ago and so completely that no traces remain for us to find. Billions of years of radiation, oxidation, and geological processing might have erased every signature. If you made this far, make sure to give this video a like, and I am sure you will love this other video on the screen. The terrifying distance to Andromeda, that dim smudge in the night sky, is hiding something terrifying about space and time. See you there.